welcome back. Thanks for having us, Dorry. Thanks for coming all the way from Baltimore.
Sure,
You
thanks
gave
for the
a
invitation.
spectacular lecture today. It blew people away. Not just because of maybe the complexity of the content, but even more so because you made it understandable for people. For the average person to understand big data and the implications of that, in your perspective, what is most relevant, important, and how can we understand the dimensions of such big data?
Yeah, I think the most important things that every single person in transplantation needs to understand is, one, how to read the literature. So to understand at least enough of the strengths and weaknesses of the data and the methods that are being used, so that we can read the literature as critical readers, not as somebody just relying on the authors to tell us what we know. And two, this familiarity with the data that are available and the methods that are available, using that to drive the next set of research questions. So there are some of us who do this on a regular basis, but there are many of us who are in the trenches taking care of patients all the time, every day, day in, day out, and coming up with new research questions that could be directly impactful on patient care. And I think that we all as a transplant community can collaborate together to answer those questions. And so if you're not even familiar with the fact that the statistics can do something, then you won't even know to ask a given question. So I think just a top-level familiarity with it in order to be able to ask the questions that then the statisticians can answer.
Talking of this, how big is the risk, given that the granularity of the data is diverse, that big data might be leading into a not entirely correct direction?
Yeah, so I see the role of big data as hypothesis generating. So we can, for example, I talked about the ESRD risk in living kidney donors. So we can discover epidemiologically that exists, and we can quantify it, and we know that it's a substantial risk, but I mean, it's a real risk, but it's not too high. And then we can say, what is causing this? Now, if this hypothesis that's generated by the epidemiology makes sense, so there's potential biological mechanisms for it, then we should dig deeper and investigate those biological mechanisms, either through smaller cohort studies or through basic science or other translational science. And so I see it as taking something that we might sort of imagine in our minds is occurring, testing this epidemiologically, and then sending us down the scientific road to better understand this. I think if we discover things in a fishing expedition that don't make a lot of sense, then we can't trust too much what we get from the big data, although we can again use it to devise a sort of more focused study. And if that focused study again doesn't make sense, then maybe we haven't really gone down the right road. But I think it's a combination of hypothesis generation from epidemiologic data, combining this with knowledge of biological mechanisms, knowledge of how transplantation works, the science of transplantation, and then taking that deeper. And once you understand it deeper, then you can swing back around and apply it to patient care.
So for at least some of these items that you identify with big data, a randomized controlled trial would sort of be the ultimate beautiful proof to say, okay, this is valid if you look at it prospectively. We understand that this is certainly not always possible, especially for some of the things that occur long term.
Right.
Do we have to live with the reality that this is the best of what we can get with what you said in addition to that?
Yeah, I mean, it depends on the research question. If it's a comparative effectiveness study and you're comparing two clinical protocols, then a randomized trial is the gold standard and is probably something that should be done based on some hypothesis we get from big data. But then even Think about, for example, the randomized controlled trials of steroid withdrawal. Now we're in the real world. So the RCTs are run on homogeneous populations in academic centers in sort of their own little world. Then 10 years later, you have all this real world data, and you want to know, did this hold true? Even if it worked in a randomized trial, did it work in the real world? And so the big data, you can come back to the big data as well. Sometimes you don't even need a randomized trial. So let's go back to the live donor ESRD example. If the big data say that there's an ESRD risk, then all you need to do is take a small group of live donors and test some of their early post-donation markers, like one of the cohort studies in the US did. It turns out that only a couple of years after donation, people start to look like they start to look like early CKD patients. And so there is now a little bit more, a stronger hint of a biological mechanism that goes along with the big data. Now, we're not going to get 100,000 patients, all of their individual, GFR measurements and all of the various lab tests that they have done until we can link to those things. But in the meantime, we can study smaller cohorts and see something that reflects the same biological mechanism that the big data implies. Now we feel stronger about it.
One of the elements with big data analysis that continues to be challenged also is the control groups. If you pick a patient population and then you have to pick a coherent control group that was equivalent as far as this can be said, it remains a matter that is always challenged. What do you say to justify that?
Well, that's the same issue for all science. Anything that's not a randomized trial, you have to come up with a counterfactual. So for a patient who got a treatment, the counterfactual is that patient who looked exactly like him but didn't get a treatment or got a different treatment. When you use big data, when you use real-world data, you have this confounding by indication that we talked about briefly in the talk, which is that people will treat a patient with A or B depending on the patient themselves. And so then when you make those comparisons, you have to account for those things. But there are good statistical methods for accounting for these things. And again, if what we find fits a biological framework, a conceptual framework of what's going on, then we feel like we're getting good confirmatory data. If it doesn't fit this framework, then we need to think about it a little bit more detail.
Well, thanks, Dorry, for your insights. Thanks for coming to Brussels. You gave a beautiful lecture. You inspired us all. I hope you will come again to Barcelona. We're looking forward to work with you again in the future.
Thank you for the invitation.